This video is part of a series of presentations covering key concepts of multithreading and synchronization. This specific presentation covers the use of multiple mutex objects with multiple resources. First, the presentation covers the use of multiple locks to establish separate critical sections. Next, the presentation covers the dining philosophers model that is often used to work with programs that need to lock multiple resources simultaneously. Multi-threaded programs often require synchronization so that threads can consistently update or write to shared memory locations without experiencing race conditions. Shared resources are similar to an intersection in a street, and that can be compared to a shared variable in a program. Similar to how we use lights in an intersection to coordinate access, in multi-threaded programs, a mutex along with a lock guard is used. A lock guard or a mutex is comparable to a lock on a door. So in a street, cars can go through an intersection only when the lights are green. Similarly, in multi-threaded programs, when a thread wants to use a shared resource, it has to and unlock the mutex after using the shared resource. Similarly, the thread has to use the shared resource, and unlock the mutex. And this operation ensures thread-safe operations where only one thread at a time operates in a critical section. Keep in mind, this approach essentially reduces a multi-threaded program to a single-threaded program in the critical section. So, when we have multiple shared resources or multiple intersections, we need to have multiple lights. This is the same philosophy we're going to look at, where every shared resource should have its own set of mutexes that are locked and unlocked. And the idea is that we maximize the opportunities for threads to utilize those resources, because if we don't do this, then only one lock will be available and the effective use of resources will be significantly impacted. So think about it, if you have multiple intersections that are controlled by one set of lights, that would be a crazy situation. Similarly, when you have multiple resources, you want to have multiple mutexes in order to arbitrate thread-safe access to those resources. So in this presentation, we'll first look at how to use multiple mutexes, but each thread locking only one mutex at a time. Then we will build on top of that, where each thread will start simultaneously locking multiple mutexes. And this is where we'll use the dining philosophers model to help us have a mental model on the operation or locking of multiple resources simultaneously. So the dining philosophers model is just an aid to help us visualize the problem better. Multi-threaded programs can and often operate with many shared resources in an environment. So for example, multiple threads may want to operate independently on different bank accounts, or you could have multiple threads that want to operate independently to print data to some printers, or you can have multiple threads that want to read or write to several different files or database tables. In such situations, having a single lock doesn't make sense because each thread wants to operate on different resources. So for example, if three threads want to print, and if they can print only on one printer at a time, then the other two printers will be idling if we use only a single lock here. So this situation doesn't make sense. Instead, what we need to do is every resource should have its own lock. So here, three threads can be simultaneously printing on three printers. Four threads can be simultaneously operating on four different bank accounts. Same way, threads could be operating independently on independent subset of files. And these scenarios, each shared resource is controlled by its own mutex, and this reduces thread contentions for mutexes and hence maximizes opportunities for threads to operate simultaneously and independently, thereby increasing the overall performance of the program. Note that std mutex is just like any other object, so you can use it anywhere in a similar fashion to string. So that means you can create a list of mutexes, or you can use mutexes in unordered maps, and that would be absolutely fine. Mutexes can be also used as instance variables in a class. So for example, here you can create a class called bank account that has a bank mutex in it. So that means every object will have its own mutex that can be independently locked and unlocked. So the general strategy with multiple resources is that each shared resource should use its own mutex. So threads will first lock the appropriate mutex of that shared resource that they want to use, then use that shared resource. This could just be a variable as well, and then unlock the mutex. So a pretty similar strategy to create a critical section. Of course, here you can use a lock guard to automatically lock and unlock a mutex, which is a very handy approach. So let's look at an example here. Assume that a large number of threads want to write data to different files. This is a very common scenario in web servers generating log files or database servers where threads want to operate on different tables in a database, so on and so forth. So here we're going to create an array of files. So here is a file list. Of course, here in this example, we are assuming there are 16 files, but n could be a different value here. We want to create a method called write, which is going to write some given data to some given file. Notice that the ID of the file indicates the file specific stream to which we want to write the data. However, note that if two threads simultaneously try and write to the same file, which might happen, we do not know what the ID value is going to be. If two threads call this write method with the same file ID, then it will cause a race condition. So we need to somehow prevent a race condition while trying to ensure maximum multi-threaded performance. So you should understand this problem. If you just have a single lock here, then only one thread can go and operate on a single file. But we want to be able to maximize the operations. So we want multiple threads to operate as much as possible on all of those 16 files. So the approach that we're going to do is not have a single mutex, but instead have an array of mutexes, one mutex for each one of those files. So you should be able to visualize this one lock per file. So given n files, we're going to create n mutex locks. Then this write method is specifically going to lock one specific mutex logically corresponding to that given file. So we lock the mutex at that given file's ID and then write data to the file. So you should be able to visualize multiple threads here. So if 16 threads are writing to 16 different files, not the same one, 16 different files, they can all simultaneously lock that corresponding file, write the data simultaneously, and unlock all of those 16 locks simultaneously. So you should be able to visualize this 16 threads independently running through 16 files, but in a thread safe manner. And keep in mind, they may not be using the same file, so they can use different combinations of the files depending on what the ID of the file they want to write to is. So in this code below, threads can concurrently operate on n different resources if possible. But at any given point in time, only one thread uses a specific given file. So that is also an important aspect to keep in mind. Of course, it's always a good idea to wrap these kinds of methods or any variables that you're using between methods in a namespace so that the namespace does not allow these variables to pollute the global scope. Keep in mind, having global variables is a bad software engineering practice, so these namespaces alleviate some of these issues. So in order to call this method in a program, you have to use the log prefix. So you would write this code as log : write to file ID number 1, the string hello. So you would call this method as with the namespace prefix. Just like we would do with std namespace, we say std : Same way here we say log : to the write method. All right, now let's look at using multiple mutexes simultaneously. So far, all of the problems that we've seen, each thread operated or locked and unlocked only one shared resource or one mutex at any given time. However, there are many programs that need to operate with multiple shared resources. So for example, a thread might need to move or update bank accounts, like move money from one bank account to another. In this case, you may have to lock two bank accounts because you're operating on two bank accounts simultaneously, moving money from one to the other. Or another situation could be that threads might want to simultaneously print on two printers to make fast copies. So here a single thread may want to simultaneously lock two printers. The key here is simultaneously. Both are being locked simultaneously. Or you could have a situation where threads may want to swap or move data between two files or database tables. Again, in this situation, you're simultaneously working on two files swapping information. So threads have to lock two files simultaneously. So the key word here is simultaneously locking. So in such scenarios, threads will need to lock multiple mutexes simultaneously. This is where the dining philosophers model comes into mind. And the dining philosophers is just a model, and it's used as a classic synchronization problem to help visualize the scenario. So it's more for visual aid. So here in this dining philosopher model, we assume there are five philosophers, corresponding to a thread. A philosopher is synonymous to a thread here. And they're sitting in a round table. That means it's like an operating system scheduler that goes around and around and schedules threads. So it's sitting in a round table corresponding to similar to operating system scheduler. Each thread or each philosopher thinks. That means they're performing some computation. That's what the thinking part of the philosopher is. Periodically, these philosophers will get hungry and they need to eat. That means in programming parlance, this is similar to a thread wanting to update some shared resource after it's performed some compute. It needs to output or write some results. Here, the philosophers need two chopsticks to eat the rice. So keep in mind, to eat rice, you need two different chopsticks. That means you need those two chopsticks simultaneously. It's not enough you pick one or the other. You have to pick both the chopsticks. You have to have locks or exclusive access to both the chopsticks. And notice that there are only five chopsticks that are on that round table. So that means somehow the philosophers have to cooperate with their adjacent neighbors in order to be able to pick two chopsticks simultaneously. So here what happens is a philosopher will pick one chopstick if possible. That means he'll acquire one of the locks. Next, if the next chopstick is not free, the philosopher should put down the chopstick that it locked. So keep in mind here the idea is you need two locks or two chopsticks simultaneously. So when you try and lock one mutex or pick up one chopstick, if the philosopher is not able to lock the other mutex or pick up the other chopstick, you should unlock the previous one that you got. If you do not unlock, the program will deadlock, or no philosopher will be able to eat, and all of them will starve. So the starvation is similar to a deadlock situation. So here the key idea is to make sure you get both of these chopsticks. You need locks on two chopsticks simultaneously. And this is the dining philosopher's model, and it's just a visual aid to help understand the situation of using multiple resources simultaneously. So here it's important to make sure that the visual of the dining philosopher, where we're taking multiple locks on how to avoid deadlocks. Okay, so you need to take care to ensure how these locks are acquired. Incorrect order of these locking can cause what's known as deadlocks, which will result in starvation. That means no thread will be able to operate and no effective work will be done. So that's what a deadlock is, where threads are waiting essentially on each other. No thread is able to release a lock, and all of the threads are unable to proceed, and the program essentially will hang. So let's look at an example how, just a simplified example how that works. Here we have two mutexes. So we have two threads. Thread 1 is going to lock mutex 1, mutex 2. Thread 2 does it in the opposite order, M2, M1. Notice that these could be based on parameters, or when we looked at arrays of mutexes, maybe we are incorrect. We are locking mutexes in different orders based on some parameters that are given to us. So there are lots of situations where this type of a operation can arise, where different orders of mutex are locked. And this order, notice that there is a mismatch in that order. Thread 1 locks mutex 1, thread 2 locks mutex 2. Because of that, thread 1 will never be able to lock mutex M2. Thread 2 will never be able to lock mutex M1, and both of these threads essentially hang, waiting for each other to unlock. So here, to avoid deadlocks, it is important to ensure that we lock all of these mutexes simultaneously. So C++14 provides a special method called stdlock that must be used to lock these mutexes. In the newer versions of C++, C++17 and newer, we can use a newer method called stdscopeLock as a replacement for stdlock, and stdscopeLock is the preferred method to use in modern C++. So let's look at an example. Consider we have a bank with many bank accounts and multiple threads are processing some transactions, and we're going to have a transact method that needs to move money between two bank accounts. Notice that here the key operation is two bank accounts. So let's look at the code. Each bank account has its own mutex. We looked at this example earlier. And then we are going to have a transact method that is going to operate on two accounts to move money from one account to another to update the balance on the account. So let's look at the implementation of the transact method. It wants to basically move money. That means debit one account and credit the other account with the same amount. So it's moving money from one account to the other. And we need to do this in a critical section because if multiple threads are operating on the same bank account, that will cause a race condition. We do not want that to ever happen. So we want this operation, addition and subtraction, debit and credit to happen in a critical section. So here, notice the key is we're operating on two different accounts, this and the other bank account. So we want to lock both of the objects simultaneously. So we use the stdlock method and ask it to lock both the uh, uh, mutexes simultaneously. And the stdlock method internally has the necessary algorithms to avoid deadlocks and successfully lock those two mutexes. So the stdlock method will block and wait until this thread has locks on both of those mutexes simultaneously. Then you can perform the operation in a critical section. And then it's important to then unlock these two accounts. So the stdlock method is important because it uses an internal deadlock avoidance algorithm to lock those two mutexes simultaneously. Then you perform the operation and then unlock the two mutexes. So it's important to keep these operations in mind. And this is important for working with two resources, two shared resources simultaneously. Keep in mind, this approach meets all of those four important rules to establish an effective critical section. That means no two threads are in the same critical section simultaneously. No assumptions have been made about the speed or number of cores and CPUs. No thread outside a critical section may block a thread in the CS. So this deadlock avoidance algorithm is important to meet that number 3 criteria. And then number 4, hopefully none of the threads should wait too long. And here we try and keep our critical section as small as possible so that threads don't wait too long to enter their critical section. So let's do a quick recap of what we learned in this presentation. We learned the idea that each shared resource should use its own mutex to maximize concurrency and performance. So you should always have this mental model of multiple mutexes, one for each shared resource. Mutexes are just like instance variables. They can be used as, in containers. You can use them in std_vector. You can use them in unordered maps. And when multiple resources are required in a critical section, we keep the dining philosophers model in mind, where we want to simultaneously lock multiple resources. So it's important to use the stdlock method, or in newer versions of C++, you can use the scoped lock. Keep in mind with stdlock, you need to unlock all of the mutexes, but with scoped lock, it automatically does it. That's the advantage of the new API. You don't have to unlock it, but with stdlock, you always have to unlock. So with C++14, you have to remember to unlock those mutexes. Let's do a quick recap. We've looked at multithreading and the basics of multithreading in C++ and measuring performance. We looked at the idea of race conditions, and then we looked at data parallel, task parallel applications, and background threads. Now we are looking at threading with synchronization with single resource. Now we have looked at threading with multiple resources. In the next presentation, we'll look at producer-consumer model for more sophisticated multithreading. Hope you found this presentation useful and interesting. Don't forget to check out the other presentations in this series.